So today's lesson is on the binomial theorem. And to learn where this comes from, we're going to do some old school stuff and give you some background information. So the beginning of the lesson, you can see, starts off with expand each of the following expressions by performing the indicated multiplications. So we're just going to go through these one by one. And what we have first is a plus b all to the 0. Well, of course, anything to the 0 power is 1. Now, I'm going to do something a little strange. I'm going to write that 1 way out here. So a plus b to the 0 equals 1 way out there. Number 2, a plus b all to the first power. Well, the first power doesn't do anything but one term, so it would be 1a plus 1b. And I'm going to write that like that, sort of trying to put everything in the center. Number 3, of course, a plus b all squared is a foiling problem, so I'm going to do a little work down here. A plus b, write it twice, times a plus b, and we would do our firsts and our outers and our inners. I put ab, and our lasts. Couldn't remember what I left out. B squared. So this is a squared plus 2ab. So there's 2 of them plus b squared. So let's get that written up here. It's actually 1a squared plus 2ab plus 1b squared. I'm writing the coefficients with the 1s like that on purpose. The next one is a plus b all cubed. So I'm not going to do this, but I could do a plus b times a plus b times a plus b and start all over, right? But my first step would be to FOIL these. So since I already know the answer from up here, I'm going to use this answer up there. So I'm going to say that these two already gave me a squared plus 2ab plus b squared. And then I'm just going to multiply that by a plus b. This could be a little bit of work, but we can do it, no problem. So a squared times a squared times b, okay, 2ab times a gives me 2a squared b, and 2ab times b gives me 2ab squared, and then b squared times a. Just going to put my a's first, and b squared times b. Combining like terms, I get a cubed plus, these two go together, 3a squared b. These two combine, 3ab squared, and plus b cubed. So that's my answer for a plus b all cubed. So coefficient-wise, I have 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed. All right, let's do one more here. It's a lot of work. A plus b all to the 4th. Well, I have an idea. I'm going to take this answer, which is this, and do it twice. So let me grab this purple pen again. I don't know if you guys have room, but I need to make more room. You can use the back of your sheet or squeeze it in somewhere. If I'm doing a plus b all to the 4th, then that's a plus b times a plus b times a plus b times a plus b. And I know this is this answer from above, because that would be a plus b all squared, and so is this. All right, so let's do our distributive property here. A squared times a squared. I'm just going to take each one of these and multiply it by the 3 in the second one. one at a time. So a squared times 2ab, a cubed b, and a squared times b squared. Okay, then I'm done with that. 2ab times the first one. Sure that looks like a plus. 2ab times the second one gives me 4a squared b squared. Try and get a step ahead of me. 2ab times b squared. And 2ab is done. And the last three, b squared times a squared. And b squared times 2ab. And b squared times b squared is b to the fourth. Okay, whew, we're done. So we have some terms we can put together. A to the fourth is all on its own. 2a cubed, I have this one, and this one is 4a cubed b. And for, let's see, that was a cubed b. There we go. 4a cubed b. For a squared b squared, I've got this one, and this one, and this one. So I've got a squared b, 1a squared b plus 4 plus 1 is 6a squared b squared. Okay, those are done. And then I've got 2ab cubed plus 2ab cubed. 4a b cubed. And last but not least, my 1b to the fourth. So I'm going to transfer that up here, writing those coefficients nice and big. So 1a to the fourth, 4a cubed b, 6a squared b squared, 4ab cubed plus 1b to the fourth. So now looking at what we have so far and kind of seeing where we're going ahead, I'm very curious about the coefficients of those terms up there. So using this up here, I see I have a 1 and a 1 and a 1, a 1, a 2, a 1. I'm just going to transfer those down here. I think you have them all on the same page, so you can just transfer them. Okay, so for the third power of a plus b, I had a 1 and a 3 and a 3 and a 1 up there. And for the fourth power is what I'm looking at. 1, 4, 6, 4, 1. And that is the last row that we did. The last one we did was a plus b to the fourth. But I want to work here now and see if we can go fill in that line up above. So do you see a pattern in these numbers? It's actually a very famous pattern. And the pattern is called Pascal's triangle. And here's the deal. I bet you know some, like, you might know this first number is going to be a 1, and you can probably tell this is going to be a 5. But how do we go from there? Because so far it's been 1 alone, and 1, 1, and 1, 2, 1, 1, 3, 1, 4, 1, 5. Well, what's this next number? So the pattern comes from, I'll tell you the hint, to get any term, for example, to get this 3 here, I only have to look above to the 1 and the 2 and add them together. To get this 6 here, I added the 3 and the 3 above it. So look above and add up the 2 numbers to the left and the right. So 5 comes from 1 and 4. What would I get from 4 and 6? I would get 10. And what would I get here from 6 and 4? 10 again. And how about 4 and 1? 5. And then we always start and end with 1. So the pattern is is to add the 2 from the line above. You might want to add a little more detail there. So now this 1, 5, 10, 10, 5, 1, that's going to be the coefficients of my next expansion. So if I want to do a plus b all to the 5th, we're not expecting you to foil out and do all this work, although we do love work. What we're going to expect you to do now is see patterns in these values. So we know we're going to have 1 and 5 and 10 and 10 and 5 and 1 as our coefficients, because that's what we've learned from Pascal's triangle. But what about the A's and the B's now? So now look at the A's and the B's in these lines and tell me what you see. I know you can't really tell me, but I hope you see that the first term in each one, and even this one, this would be a to the 0. The first term in each one, right, is the first item in the parentheses to the power. So here I'd get 1a to the 5th plus. All right. You might also notice, since we did the first term, you might notice that these last terms are the second term in the parentheses, also to that highest power, b to the 5th. Okay. Now look at the line above it or the line above that. Check your theory. What happens to the A's and the B's from there? So from here, the a to the 4th example, the a goes to 3, a squared, and then a to the 1st, and then actually a to the 0. So the a's start out with the highest exponent, and then they work their way down. So let's fill those in. 5a to the 4th, 10a to the 3rd, 10a squared, 5a to the 1st. All right, those worked out nicely. And now how about the b values as we work our way up? Let's see. This is really b to the 0, b to the 1st, b to the 2nd, b to the 3rd, and of course we already knew the last one's going to have the highest exponent. So the b's start at nothing and then work their way up. So I could put b to the 0 here. I usually don't. B to the 0, b to the 1st, b squared, b cubed, b to the 4th. And the only other thing I'm missing is, of course, this is an expansion of terms, and we would have addition between our 6 terms. So there you go, you're done. A plus b all to the 5th can be figured out if you know Pascal's triangle and the pattern of the a's and the b's with their exponents. Very colorful. I think we have another one on the next page. So you might have to switch back and forth here. What are we going to get with a plus b all to the 6th and a plus b all to the 7th? So you go ahead and pause the video, see if you can do that a plus b to the 6th, and then come back and see if you're right. I'm just going to throw a quick Pascal's triangle on my chalkboard so I can use it. All right, so I'm looking now. I know I'm going to get 15 for the next coefficient. And that's just going to come from the previous page. The next item here would be 1, and then 6, and then 15, 20, 15, 6, and 1. So I know that's what I'm getting. Oops, too far there. And I know my A exponents are going down and the B's are going up. Notice each time though the exponents add up to 4 and 2 adds up to 6, 5 and 1 adds up to 6, and 6 and 0 adds up to 6. And that's the power that you're raising this expansion to. So we've got as our next term, the fourth term, 20, a to the third, b to the third, plus 15, a squared, b to the fourth, plus 6, a, b to the fifth, plus 1, a to the 0, b to the 6th. All right, hope you got that. Check. You can always go back through and just sort of check as well. It was a 6th power, and you've got 6's adding up with all your exponents, so you didn't mess that up. Your coefficients are 1, 6, 15, 20, 15, 6, 1 from Pascal's triangle. And the powers of your A start at 6 and decrease. 6, 5, 4, 3, 2, 1, and then 0. And your powers of B start at 0 and increase. 0, 1, 2, 3, 4, 5, 6. All right, let's try the next one. I should write a little smaller. Oops, that needs to be a 5. Apologies. And then we have 7, a to the first, b to the 6th, and then we have 1, b to the 7th. There you go. So we no longer have to FOIL, I guess. All right. So it's not always possible or easy to use Pascal's triangle. I think it's easy to jot it down real fast. But in order to use a theorem to find the expansion of a given expression, we need to know a couple of other things. So we've actually already covered n factorial. And n factorial is equal to n times n minus 1 times n minus 2. And you keep multiplying all the way down to times 1. So it's the product from the number down to 1. So 2 factorial is actually 2 times 1, just 2. 3 factorial, 3 times 2 times 1, that's 6. Go ahead and do the rest of these. Pause, get ahead of me. Also, special case, 0 factorial is actually equal to 1, and 1 factorial is equal to 1. And we don't do factorials of negative numbers. So now another special symbol that we saw when we did combinations. This n over r sort of looks like a fraction. N and r need to be integers, so no decimals, no negative numbers, and n is always bigger. So n choose r. This is n choose r. It's the same as a combination of n things taken r at a time. The connection that we're going to make here is that Pascal's triangle is actually n choose r. So the formal definition for n choose r, I'll give you in a moment. Let's do a couple of these. 5, oops, I'm looking at the wrong one. 4 choose 2 is going to actually be 6. And there's a couple ways we can get that. 4 factorial divided by 2 factorial, and then also divided by 4 minus 2 factorial. So this would be 4 times 3 times 2 times 1 divided by 2 times 1 times 2 times 1. And we can reduce these and see that we get 6. So the formal definition, which in your calculator does it for you, is that it's n factorial over r factorial and then n minus r factorial. So 5 choose 3 is going to, let's do it the long way this time. 5 factorial over 3 factorial, 2 factorial. Write it out. 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1, and then times another 2 times 1. It's kind of cool because most of these you can always cross a big chunk out, and then on the top you have 20 divided by 2, and it's 10. Okay, so we've actually already done these because we've done combinations at the beginning of the unit. What this is meant to tie into is Pascal's triangle again. Pascal's triangle, when we wrote it as, I'm going to use a thick marker, we wrote it as 1, 1, 1, then 1, 2, 1, and 1, 3, 3, 1, and 1, 4, 6, 4, 1, etc. These values, 3 is equal to 3 choose 1. Whoops, I'm trying to erase that. And 3 is equal to 3 choose 2. And 4, this is 4 choose 0 and 4 choose 1, and 4 choose 2 and 4 choose 3 and 4 choose 4. So these are actually, again, representing the coefficients of the expansion for binomials. So I'm going to just say 0 choose 0 is 1, 1 choose 0 is 1, and 1 choose 1 is 1. 2 choose 0 is 1, 2 choose 1 is 2, and 2 choose 2 is 1. 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3, 3 choose 3 is 1. And then if I did the next line, it would be 4 choose 0, which is 1, 4 choose 1, which is 4, 4 choose 2, I'm putting the answer down, which is 6, 4 choose 3 is 4, and 4 choose 4, running out of room over here, 4 choose 4, which is 1. So we can get Pascal's triangle in a lot of ways, and one of them is the combinations as well. All right, amigos, the binomial theorem is actually on your reference sheet. It's down right above the normal curve, and it says a plus b all to the nth power, so any power, equals n choose 0, a to the n, b to the 0, plus n choose 1, a to the n minus 1, b to the 1, plus n choose 2. So this is all there. A to the n minus 2b squared plus. And now it just goes, all right, let's skip to the end, dot, dot, dot. N choose n would be the last term. A to the 0, b to the n. This is not doing anything new that we already did this on the first page. Let me point a couple things out to you. We've now learned that our coefficients come from the Pascal's triangle, and they come from combinations. So you're going to take this n, and you're going to do n choose 0, n choose 1, n choose 2, and all the way up to n choose n. Then your first term, whatever this is, you're going to raise it to the nth, and then 1 less, and then 2 less. And the powers of your a's, remember, decreased as you went along, all the way to nothing. Then you take the second item in your parentheses, and you start it at 0, and make it go up 1, up to 2, all the way up to that maximum value. So this theorem that's written out for you, not a lot of kids use it. If you're stuck, you can certainly look at it, but it looks really tough. It's still just what we did. Let's try some examples. First one is x plus y all to the 6th. So I'm just going to churn this out like a factory. I know that my n is 6. That's the power you're working with. So to expand this, I'm going to do 6 choose 0, something, something, plus 6 choose 1, something, something. I'll come back to those. Plus 6 choose 2, something, 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 something. 6 choose 3. Gotta leave yourself some room. I'm gonna run out of room. 6 choose 4. Couple more here. I'll put them down here. 6 choose 5. 6 choose 6. Now what am I putting in these parentheses? I'm just going to use a different color. Well, the first item in my parentheses goes in the first slot. So now I'm dealing with x's all the way here. First slot. And I know that the exponent on this starts out at 6 and decreases. 6, 5, 4, 3, 2, 1, 0. I know in my second slot, which is green, I grab whatever's here. That's a positive y, so it's going to be y all the way down. And I know that that exponent starts at 0 and goes up. And remember, my exponent should always add up to 6, because that's my n value. All right, now that we've got everything filled in, that was sort of like an assembly line. Now that we've got everything filled in, I'm going to just move this over a little bit. Can I move that? No, I guess not. I'm going to evaluate everything. So remember, where do my coefficients come from? 6 choose 0. I could go and do it on the calculator, but I could also have a quick Pascal's triangle jotted down. 6 choose 0 is 1, and I've got x to the 6th, and y to the 0 is 1. So my first term is 1 times x to the 6th times 1, just x to the 6th. That's done. My next term is 6 choose 1. Pascal's triangle, it's the next item. It's 6, x to the 5th, y, and I'm done. 6, x to the 5th, y. Next term, 6 choose 2. I should just do them underneath, I guess. These aren't as tough. Plus 15, x to the 4th, y squared. Done. Plus 6 choose 3. It's 20. X to the 3rd, y to the 3rd. Done. Isn't this fun? 6 choose 4. 15. X squared, y to the 4th. Done. Can I squeeze them all in? Plus 6. X, y to the 5th. Done. Plus 1. x to the 0, 1, y to the 6th. I can't fit it all in. And there is my expansion of x plus y all to the 6th. Now they get a little tougher, so I'm going to do 1 or 2 more here. I know I'm already at 30 minutes, but this is a big important lesson, so I don't feel bad. But good news, this is an n value of 3. So I'm curious, with an n value of 3, how many terms will I have? As a clue, look at the one above it. I had an n value of 6, and I have 1, 2, 3, 4, 5, 6, 7 terms. So you always get one more term than your power because of those zeros. So here I had 7 terms. Here I'm then going to have 4. So I won't have to squeeze as much. All right, so let's get our assembly line out here. 3x plus 2y all to the third. So 3, choose 0, something in there, plus. 3, choose 1, something in there, plus. 3, choose 2, something in there, plus. 3, choose 3, something in there. All right, now what goes in there? This one's a little different, because the first item in my parentheses is 3x. Ooh, 3x. And our exponents are going to go 3, 2, 1, 0. And in the second slot here, I have positive 2y, so 2y, and I'm going to have my exponents increasing. 0, 1, 2, 3. So we have a little more work to do this time. Because, for example, when I do 3x all cubed, I got to make sure I cube everything. 3x squared, square everything. So there's a little more work on these. We just have to pay attention. 3, choose 0 is 1. I might just steal all the values off of Pascal's triangle. This is 3, that's 3, and that's 1. So those parts are done. 3x all cubed is 27x cubed. 2y to the 0 is just 1. So my first term is 27x cubed. Next term, I had a 3. 3x all squared is 9x squared times 2y. So I'm going to do this whole term. That's 3 times 9 times 2. So 54x squared y. That one's done. Plus. Okay, I had 3, and 3x all to the first is 3x. 2y all squared is 4y squared. And all together, multiply, 36xy squared. And the last term was 1 for the combination of 3, choose 3. 1 for 3x to the 0. And 2y all cubed. Remember, that's 2y times 2y times 2y is 8y cubed. And we're done. That's the answer. You are expanding without all that foiling and distributive property and all that messy stuff. Please don't combine any of these terms. All of these terms are different. This is x cubed. This is x squared y. It's different. Xy squared, different. And y cubed, very different terms. Don't put those together. All right. You can pause if you want. I would try the last one here. I'm going to do number 3. And you can pause and check it. But I'm going to walk through it again one more time. Then I'll be done. So my n value is 4. That's my exponent. So I know I will have 5 terms I start my combinations with that 4. 4, choose 0, something in each set of parentheses, plus. 4, choose 1, parenthesis, parenthesis, plus. 4, choose 2, I want to make sure I have enough room, parentheses, parentheses, plus. 4, choose 3, and 4, choose 4. Okay. What goes into parentheses? So I'll grab a different color. 3p is first, all the way down. 3p, 3p. And my exponents start at 4, 3, 2, 1, and 0. And now my second item in my parentheses, this time I have subtraction. So we have to add that negative in front of our 4q. Negative 4q, negative 4q, negative 4q, negative 4q. Exponents here, start at 0, 1, 2, 3, 4. All right. Now think ahead. Is it going to make a difference on a negative 4q if you have an even exponent versus an odd exponent? The answer is yes, it's going to make a difference. If you have an even exponent, it's going to come out positive. If you have an odd exponent, it's going to come out negative. So be aware, that is going to happen anytime we have a negative or subtraction in our original problem. All right, let's finish this one up. 4 choose 0 is 1 times 3p all to the 4th. 3p, 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 3p is 81p to the 4th. And whoo, catch a break anytime there's a 0. That's going to be times 1. 4 choose 1 is 4. 3p all cubed is 27p cubed times negative 4q. To the first is just negative 4q. 4 choose 2 is 6 times 9p squared times, we did this one right down here, 16q squared plus 4 choose 3 is 4 times 3p times, we did this one down here, negative 4q all to the 3rd is negative 64q cubed. I'm losing track of my p's and q's here. 4 choose 4 is 1, 3p all to the 0 is 1, and negative 4q all to the 4th is going to be positive, and that's that 16 times 16, 256, they tell me, q to the 4th. All right, so let's do one more swipe through and polish up these values. That's 81p to the 4th. All right, I'm going to grab my little calculator here so I don't make any mistakes with you guys. What do I have here? I have, first of all, want to notice I have a negative in that one, and I have a negative in this one. That's going to affect the overall sign of the term. So instead of addition here, I'm going to change it to negative because it would be adding the negative. So I have 4 times 4 times 27. That's 432 p cubed q plus 6 times 9 times 16, 864 p p squared q squared. Let me try that one again. 54 times 16. Yep, okay. This term has a negative in it, so it'll end up being adding a negative. And I said before I would just put subtraction there. Adding the opposite or subtraction, that's the same thing. So here we have 4 times 3 times 64 for the coefficient. 768, that's a p and a q cubed. And last but not least, 256 q to the 4th. So this one ends up with, now I'm going to erase those, adding the opposites and just put in subtraction. Every other term turned out to be negative. If you think about it, this first one's positive. 81 p to the 4th minus 432 p cubed q plus 864 p squared q squared minus 768 p q cubed plus 256 q to the 4th. All right, woo! See you tomorrow.